Hi everyone, and welcome to the second of our HPC Perspectives Live. My name is Sharon Howe and I'm your host today. In the first episode, we got to know Agnes Brideau and she shared some of her insights and vision for the future. And we ended with reflecting on International Women's Day. That interview is still available on YouTube if you missed it. It's been a popular one, so it's worth digging out. Over the next few months, we'll continue to host some discussions and introduce you to a number of people. I'm not quite sure whether, everyone can hear me, I think. So I'm not seeing a stream, but hopefully it's working okay. Someone will let me know if not. But over the next few months, we'll continue to host discussions and introduce you to a number of people across our group who bring their insights into different aspects of our HPC and cloud solutions business at CDG, and as well as the teams and technology that make that happen. Today, I'm pleased to welcome Laurent Clerc, our CTO. Laurent, thanks for joining us here today.
Hey Sharon, thanks for having me.
Great. So this month's focus is on technology development and deployment. The HPC and wider compute industry is continually innovating, and we're inundated with the news of novel developments and product launches of kind of exciting looking shiny things. And here at CGG, we're kind of well known for continually innovating into what is a production environment. And we'll look at what that means for our compute hubs and HPC team. But first, let's start with yourself, Laurent. You've been with CGG on this kind of technology journey, as we'll describe it, for a few years now. Tell me about the first roles you've had and the roles you've had over those years. Where did you start off?
Well, Sharon, it's kind of a long story. As you said, I've been with CG for a few years. I started in 91, so quite some time ago. And at the time, the company was sending people to the field, as they used to call that, which was land acquisition crews. And I'll come back to that because there is a story about how innovation in those places really happened. So CG has been doing that for a long time. But after a few years of land operations, I went back to my original calling. I'm an engineer by training and specifically in the IT field. And I ended up managing various teams that did software and then hardware development and then design of data centers for CGG. And then eventually I managed the HPC, the high performance computing activity for close to 20 years. And as we embarked into creating a new business around HPC and cloud, I became the CTO, the Chief Technology Officer. And what that means essentially is that I'm now looking at everything that we need to do to stay on top from a technology point of view for the next few years.
So what does that involve on a day-to-day basis, Laurent?
Well, that involves mostly doing what we call technology scouting, which means being aware of all the new trends in all the new activities or technologies that could have an impact on what we're doing. And I must say that in IT, that's a pretty big task. It used to be when I started that IT was a fairly small thing, like 30, 40 years ago. But now there are so many different aspects of IT that staying on top of that is very difficult. So I rely on a team of people that help me do that, and that are capable of finding what is the next thing we should pay attention to. And then, in addition to that, obviously, once you know what to pay attention to, then you have to organize yourself so that you can acquire that technology, test that technology, make sure it's going to blend well with what you're already doing, the operations that we have. We're an industrial company, so what we need to do is make sure that the technology that we acquire actually works for the business that we want to deploy. There is a feedback loop there. Some technologies will suggest a new business. Some new businesses will require new technology. So it's not a one-way street. There's a lot of discussions occurring within the company to try and map the strategy for us for the next few years. So that, in a nutshell, is the job of, it's my job, and that's what I think a CTO should be doing in the context of a company like ours.
Excellent. So let's go back to the beginning then and look at CGG. And I think we can all give some examples of the novel developments that we might have seen in our own lives due to the advancements of computing technology. You know, I'm sure we can all remember our first mobile phones, for example, first laptop. But within CGG, what are those kind of key milestones in our history to do with technology and computing?
So I'll get to that, but I wanted to add that CGG has been innovating technologies way before we started using computers. The business of acquiring data, so seismic processing, is all about sending sound waves in the ground and then recording the echo of that. And all of the equipment that is used for that, so we do have a subsidiary called Cercel that produces world-class equipment for both recording and generating sound waves, and that technology itself keeps on evolving. And then the way you use it in land crews is very ingenious as well. You have to adapt to the environment, and it can be at sea, it can be in remote places of the globe. And I've witnessed myself at the beginning of my career how much ingenuity goes into using all those technology, how much thinking out of the box, if you will, goes into that. And obviously, when we started doing processing, the same thing happened. We needed computers to do things that people hadn't done before. And the very first computer I remember, and for those of you who like that sort of thing, you should go and Google it, was a Perkin-Elmer, which was barely a computer, to be honest. It was a fraction of what an iPhone can do today. But that's how it started. And then, of course, after that, we started, and that was way, well, almost, in the 50s. And then after that, we started having some of the largest machines that existing on the planet. We had the original Crays, the original Convexes, for those of you who remember that. These were huge machines. And again, they're a fraction of the processing power that you have in your hand now. And then we started deploying smaller machines, the Sun Enterprise, the Origin 2000s, the IBM SP2s, some of which were deployed in vessels, so boats, doing acquisition and QC on board. And then after that, around 99, we started looking at new technologies again because something new was coming out, the Beowulf clusters, for those of you who remember that. And they weren't pretty, and you had to build them in your garage, basically, because there was no support for that. But we adopted it, and in 99, 2000, we started using them for processing because they were so much faster and cheaper than the machines we had before. And then around 2009, we started looking at GPUs, so graphic cards for processing. That was the very, very beginning of things like CUDA. And we adopted it almost immediately because, again, it was a lot faster and a lot cheaper than what we had before. At the same time, we started realizing that heat load was an issue. Those machines were getting hotter and hotter. So we started looking into immersion cooling, where you dip servers in a bath of mineral oil. That happens to be liquid, so it removes the heat very well, but it's not conducting the electricity, so you don't create interesting things when you dip the servers in that. But all that to say that continuously, when we see a new technology and we think it can work for a business, we adopt it and we put it in production.
You've given some great examples there, Laurent. I mean, I think there's some early examples of edge compute right there in terms of the deployment of that compute on the onboard vessels and on land crews. They're really quite harsh environments already, aren't they?
Yes, and that's a great point, Sharon. You know, people talk about edge compute, they talk about machine to machine, they talk about big data. All of these are things that we've been doing all along before they even had a name. We handle a huge amount of data. We have a remote processing capability all over the place, distributed all the way up to the recording equipment, and we have thousands, literally, of those boxes on a given crew. And obviously, we also had QC machines that could be fairly large on vessels and on land crews in order to make sure that the data that was acquired was of quality. And so, yes, we've always had the capacity to move a lot of data, to communicate with a lot of devices, and to do that all around the planet at the edge and bring the data back in our data center, so you can call it the core and process it. So that architecture is something we've always had. And it's interesting to see now that a bunch of other industries are catching up with that and are beginning to do the same thing.
It sounds like a bit of a similar story with the kind of the immersive cooling topic. I mean, that was a topic for us going back 10 years. Why is it such a massive hot topic at the moment?
Well, it has to do with how you cool equipment, and I'm talking about computers, and mostly the CPUs, the GPUs, but also soon some other pieces of the equipment. What happens is as the processing capacity increases on those components, the heat load, the heat they generate increases. And the traditional way to remove heat in systems is to blow air through them. And air can only remove so much heat before you get to a point where you cannot push more of it through a system, or the temperature of the air at the exit is so hot that you are frying the last of the components that's in the stream of air. And so we realized that as soon as we started using GPUs are hotter components and traditional, I would say, traditional IT components. And so we needed a better way to cool that, and going to a fluid instead, well, going to a liquid instead of a gas does increase by an order or two of magnitude the capacity to remove heat from systems. And so for us, as we moved to GPUs, the logical thing to do was to also improve the cooling characteristic of our systems, and we chose full immersion in oil baths because it's a very simple technology. It works really well. It's a very good industrial compromise. You can use standard products. You can put them in oil, and now they're cooled a lot better than they could be in air. Typically in air, when you get to about a kilowatt per 1U, so 1U is a pizza box form factor, the traditional thing you find in racks. When you get to about a kilowatt of heat per 1U, it becomes difficult to cool it with air. With liquid, you can go much faster, much further than that.
So
So
how did
that
you get that all started in CGG? Did you find it? You talked about it was just the kind of logical process, but if it was logical process, I think we'd see a lot more of that around. So why was it logical within CGG? Was it easy to find traction for these kind of ideas, which must have seemed a bit crazy at the time?
well, we're very data driven in the way we look at things, and so finding the right answer is not very complicated. You look at the data, you find the answer, and you're right. After that, you have to implement it. And implementing it is a bit more difficult because when ideas are really out of the box, people are going to look at that and say, well, that's crazy. That's never going to work. Well, dipping servers in oil was one of those ideas that was kind of hard to explain. And I have to say that even for us, the first time, so I work with a colleague of mine, Dr. Blanc, Jean-Yves Blanc, who's doing our IT strategy, and we typically visit trade shows such as supercomputing and others on a regular basis to get ideas, and we go to the darkest corners of those trade shows to see what's coming, what new idea is out there. And that's how we found about liquid cooling. And the very first time we saw that, so it was a supercomputing in 2008 maybe, or 2007. And we saw that a little startup in a corner that had a big tank of liquid and that was dipping servers in there. And we looked at each other and we said, that sounds dangerous. Well, as it turned out, that technology works really well. But yes, when you see it first, it's not very natural to want to put electronics in a liquid. And also, once you understand what it is, it's mineral oil. We had some unkind comments from various people saying, well, you're turning into one of those franchises making burgers, and you're dipping your servers in oil instead of some other product that's yellow and that you can sell in those franchises. So yeah, well, it was kind of difficult, but fortunately we had a boss at the time who was very understanding that new ideas come in all shapes, and that if you don't try them, you're never going to succeed. So basically, he told us, go ahead, try it, see what happens. And that's how we started.
So tell me a little bit more about that process of getting these things from really that concept idea into this industrial kind of commercial environment.
Yes, and that's also a good point. CG again is a very mature company in terms of adopting technologies, but we've always tried to adopt um, really innovative technologies before they are quite ready. So there is a certain amount of risk in doing that. And in order to de-risk that situation, what we typically do is we go through a two-step process. The first step is to build a proof of concept. And the idea behind the proof of concept is to um, is to basically validate that the idea works. And so at that point, we do that in a lab and we put together whatever is required so that we can guarantee that the idea works. But we've learned the hard way that if you go from proof of concept to industrial usage, there is usually a step that you need to take in order to avoid having catastrophes. And that's the industrial prototype. The industrial prototype is where you look at things like the cost of acquisition, the cost of running, the supply chain issues, the integration of your solution into what you already have, how are people going to react to it, all of the nitty-gritty details of I'm moving from a good idea to something that actually works at scale. And that's typically how we do those things. So we start with a proof of concept, which is a little thing in a lab that's going to tell you, yeah, it works. Then we go for an industrial prototype that is going to de-risk all of the aspects of going into production. And once we're happy with that, we go to full production with it. That has worked well for us, and that's how we did with oil cooling as well.
And how does the organisation support that? And what about the people? Is there a kind of, I can imagine there's a bit of a particular mindset that might be needed in some of those different groups as well.
Yes, very. So typically, we're organized in I'm going to call that an R&D, a small R&D group who does the proof of concept, and then a fairly large production group who's in charge of running operations. And whenever we move from a proof of concept to an industrial prototype to a full implementation, those people usually are part of a team that is going to put that together and make sure that everything works so that we can seamlessly transition from an idea to an actual tool that we use on a daily basis. But you're right. It does take people with a bit of an open mind to failing because you are going to fail. Not everything works, and it's normal. Of course, you cannot fail all the time. That would be a problem. But failing from time to time is healthy. Recognizing that an idea that you worked a lot on isn't going to work is difficult, but you have to. And recognizing that an idea that you worked on works and needs to be deployed is equally difficult because, again, some of those ideas are a bit out of the box. And so you have to have people that are ready to do that have that mindset.
So I think generally about 90% of innovations fail. Do you see the same statistics within the things that you try out? And how do people cope with failure?
Okay, well, we don't see 90% failure. We've been lucky or good, but we see a much better ratio of success in the things we try. That's probably because we're very focused in things we understand very well. And so we're not trying things that are not related basically to our daily activity. But yeah, we do fail. I would say about half of the ideas don't make it into production for whatever reason. And it's difficult. It's difficult mostly because people are invested in those ideas and they spend a lot of time. Fortunately, the company as a whole recognizes that risk taking is okay and that failure is part of a process. And not just in our team, by the way. We have other teams designing algorithms, designing all sorts of other things. And the same attitude prevails throughout the company. It's okay to fail. Now, in terms of personal reaction to that, well, I've been on the receiving end of a few projects that failed. And it's always difficult to realize that that's not going to work and to say, well, I just spent that many hours and that much enthusiasm on that project, and now it's not going to happen. But hey, you just terminate the project and move on to another one.
Yeah, I like the quote from Thomas Edison. I think he said, "I have not failed. I've just found 10,000 ways that don't work." And sometimes that it's a kind of could be maybe a commercial failure, but a technical success in terms of understanding when something needs to be left behind. So where do those ideas come from? I mean, you talked a little bit about rooting around at conferences. So is that partner ecosystem kind of important to a lot of those ideas, or do those ideas come from our internal groups? What do you say on that?
Well, I like to say that most of the good ideas come from your shower, because that's usually when you think about them. But more to the point, yeah, we do have a network of people that we work with. We go to trade shows, not just any trade show. We go to trade shows where usually you have an innovation corner, really small startups that have ideas and are going to try and explain that to you, because usually that's where good ideas come from. They may not succeed at first, but eventually those ideas are going to come out in one way or another. And also we have an extensive network of contacts in fairly large companies that produce components, that produce servers, that produce IT equipment. And that's a historical thing, if you will. About 20 years ago, HPC was a very, very small business, and we were some of the biggest players in that business. That was before the cloud. That was before, those massive installations that you find today. At the time, we were some of the key players in HPC. We still are, but now we're dwarfed again by much larger installations that do other things. And so we acquired a network of contacts at that time, and the capacity to go and test products way before they're available. Think of us as a Formula One team, right? We test and break products before they make it to your car. Well, in HPC, there is kind of the same sort of situation where some users are going to be a bit more capable of finding what those products can do, where they break, how they should interact with the rest of the ecosystem. And so we've been lucky to be able to work with extremely large companies doing that, and that gives us access to technology under NDA, obviously, because they don't want everyone to know. But that gives us access to this technology and give us the capacity to evaluate if and how they would work for us.
So as part of that evaluation process, I mean, what are we looking for in that assessment? What criteria are we using to assess whether or not we can move something to the next phase of prototyping?
Well, again, the very first phase is the proof of concept. Is it doing what it's supposed to do? And that's something that you really need to check, right? Because some ideas look good, but they don't produce anything. The second aspect is how much work is there going to be to put that good idea that does what it's supposed to do into an industrial context? And that's a complicated question, because you have both technical and non-technical aspects. Some of the non-technical aspects are, can you procure this piece of equipment? Can you pay for it? Can you afford it? Because we are a business, so we cannot afford to, it's not a beauty contest. We cannot afford to have the best and brightest piece of equipment, even if it works really well. I would love to, but if we did that, we would probably die as a business. What we need is the right answer. That is something that has a price point that is compatible with what our market is going to be able to accept. And then in addition to that, there is the human aspect of it. If you present something that's widely different from what people are used to, maintenance teams or even users, you are going to have to make sure that they can use it, that they want to use it, that they understand it, that they are going to be able to produce with it in a way that makes sense. So these are all the aspects that are checked out in the industrial prototype in order to make sure that product will actually integrate into our environment and do what it's supposed to do for our business, for industrial HPC.
So, we're constantly bringing new technology into these data center environments. So how does that differ perhaps then from people who also might have HPC on premises, who might be more on an investment cycle?
Well, so HPC comes in many flavor. I don't really think it's a homogeneous market, and it falls into one of two very broad categories. One is a category of HPC suppliers that have to deal with a multitude of users. So typically, for example, a university, right? They are going to have a bunch of students doing different things on that, or a national installation where they are going to have a bunch of different users coming to it and doing different things with it. And so they have to have a very an architecture that's very open to all sorts of different things. So essentially, they have to make sure there are no bottlenecks that are going to develop for one or the other of the activities, and that's expensive. That's typically creates a very, very expensive piece of hardware. And then you have HPC users like us that are industrial users that can narrow down the usage of the equipment to a type of activity. And furthermore, in our case, we control the software completely. So we can also, there's a feedback loop between how the software is developed and how the hardware is acquired. And so that gives us the opportunity to select very carefully the equipment that we use. And when we do that, we end up with solutions that are usually more efficient in terms of price performance than a generic HPC system would be.
Oh, that's great.
I do have a question. I
Yeah,
do have
no,
a question in the stream. I can answer that. Somebody's asking, does the mineral oil have to flow in and flow out of the stream, or is it a static pool? No, it's not a static pool. It flows through the servers, a bit like air does. And there are different mechanisms to do that. Usually it's pumps of some sort that are pumping oil through the server, because that's the only way to remove enough of the heat. Sorry, Sharon.
no, that's fine. Maybe while we're on the topic of immersion cooling, I don't think we've probably quite finished it yet. But why the slow uptake, and maybe why is there so much interest in it now? 10 years on.
Well, so it's the combination of two things. First of all, mineral oil is not glamorous technology, like I said. I mean, again, we had comparisons with unglamorous things, and so it's a bit of a difficult step for some people to take. And second of all, there is a financial reason why you would use oil. I mean, if you do not generate enough heat, if the heat density of your system isn't high enough, then there's no reason to use mineral oil or any other liquid cooling technology for that matter. It's only when you get to a point where components get hot enough that it makes financial sense and from a technological point of view as well to use a liquid. And so that only happens, it happened for us when we started using GPUs. But today you can see that the components are going to start getting hotter and hotter. The CPUs, the GPUs, possibly even the memory, some other pieces here and there on the motherboard. And so it is beginning to make sense for people who want to maintain density to start thinking of going to liquid cooling, and specifically mineral oil in full immersion. There are other techniques, by the way. There are 2 or 3 other techniques that are going to deliver the same benefit, if you will. And they're all going to probably have to be developed in order for us to be able to use the high density components that are coming out.
I guess the overall setup isn't the only consideration. I guess if we've got a focus on energy, then there are other areas that we can optimize as well.
Yes. So energy is the name of the game. First of all, because energy is expensive and getting more and more expensive, or more and more unpredictable in how expensive it is. And also because we have a mandate or a duty, I would say, to use energy well and not waste it, and not just create heat for lack of optimization. So the focus on trying to use energy well is very significant. So oil immersion is just one part of it. Actually, the data centers we're designing now are designed from the ground up to be efficient with liquid immersion cooling, which is something new. But also we're beginning to look at programming for efficiency. It used to be that optimization was just how much compute can I cram in a piece of hardware, how much can I get this piece of hardware to produce. And it was fine because the cost of the hardware was the driving force. Well, now that energy cost or energy usage is the driving force, it makes sense to start optimizing for energy usage. That is, instead of how much can I produce with this piece of hardware, The question becomes, how much can I produce with this kilowatt, for example? And that's a different type of optimization. And we're only scratching the surface there. I mean, some people designing cell phones and laptops and generally machines that have very little power available to them have been doing that for a long time. But in HPC, it's a bit of a new, not a new idea, but it's gaining traction. Let's put it that way.
So we've got data centers are obviously an important topic now, with UK Southeast becoming operational later this year. Is that going to be using immersion technology as well?
Yes, and so designing a data center is a fairly expensive proposition, and typically a data center, given architecture of a data center, is good for 15 to 20 years. So oil cooling is younger than that. So most of the data centers that we have today have been modified to use liquid cooling. Well, we now have the opportunity to design them from the ground up to use liquid cooling and be more efficient than what we could do before. So that's what we are doing. We are designing those data centers so that the main cooling technology, instead of being air that circulate through the servers, will bring the liquid as close as possible to the servers through immersion cooling or other techniques. So air is no longer used as a media to exchange heat in those data centers. And having the ability to design things from the ground up all the way from the data center to the software gives us all of those levers that we can play with in order to optimize the efficiency of the systems.
Tell me some more about that. How are we managing to take into account some of those ESG demands of the future? When we're looking towards sort of net zero by 2050, PUE decreases. What else can we do in our data centers?
Okay, so there are three things basically. One is, as you said, try to improve the efficiency. So there are two aspects of that. One is to improve the coding of a job so that, again, they produce as much for a given amount of energy as possible, which we're doing. The second one is to improve the efficiency of the data center themselves, and that's the PUE. So the PUE is the ratio of all of the electricity going into a data center divided by the electricity that's really used by the compute system. So typically it's supposed to not be less than one because, well, for obvious reasons, even though you can actually create virtual PUEs of less than that if you resell some of the heat, because then you get credit for the electricity. But let's not go there. So reducing the PUE down to one is, of course, a target. It's difficult. It requires some interesting cooling strategies. But at the end of the day, you're still throwing out energy in the environment, and essentially it's only used by the computing system. So the real answer to that is to try and find some way to resell that heat that you generate and use it for something else that's useful. So in other words, not just generate heat and throw it away, but have someone use that and use it for something that they would otherwise require energy for. The challenge of that is that it's difficult to carry heat very far, so you have to have people that are going to use it fairly close. And also the heat we produce is not extreme, and so there's a lot of industrial processes that require fairly high temperature that are not going to be able to use that. So it's a game of trying to find what are the proper usage of the heat that we generate within a distance that's actually acceptable. And so there are those three aspects: optimizing what you do with the heat, optimizing the design of the data center itself, and finding some way to reuse the heat that you generate.
That sounds like a good challenge to find some novel solutions for the future. We'll keep an eye out for those. But looking forward now, what else are you excited around the kind of future? What solutions do you think are kind of right around the corner?
Well, there's the elephant in the room, things like generative AI that just came out. So that's not a new thing. It's just something that was happening underground, if you will, and then all of a sudden everybody's talking about it because it's visible. I believe that in IT there are a lot of those technologies that are just waiting for the right moment to explode. Well, this is one of them, definitely. Things like quantum computing, the forever next technology that has been around for a while now, which well, may or may not turn into something useful. So you have, I would say, probably about half a dozen of those technologies that are nearing the point where they are going to be visible and perhaps usable. And so the idea is to monitor them and again design proof of concept when we think they are ready for usage.
And what about anything specific from the hardware manufacturers?
Well, the generic trend today is more heat, unfortunately, and so that's something that we're going to have to deal with, and I've already discussed that. The other is I don't know if you recall when the very first CPUs came out, they didn't have floating point units in them. There was a component, floating point accelerator, that was next to them. And then eventually that was merged into the CPUs. And then you had vector units that were outside in array processors. And then that was merged into the CPUs. And then you had various other things. GPUs, for example, are co-processors of a sort. Well, you can see that the technology of processor is beginning to absorb that. And then you have the TPUs that are used for machine learning. So you can see that the CPUs are getting more and more complex and are integrating more and more technologies that come from the various use cases that they are developed for. And so I'm expecting that we're going to see a lot more of that in the years to come. And finally, there is also another aspect, which is the interaction between machines and humans. The mouse and keyboard and screen have been around for a long, long time now. And I think, personally, I think we're overdue for an evolution of that that would provide a better interface. So generative AIs are one of the ways, because you can talk to machines now, you can even show them things. But that's still not a very tight integration between humans and machines. So I'm expecting to see something better come out. Not sure when, not sure how. Maybe Neuralink will be one of those changes, but we'll see.
Oh, no, excellent. Thanks for sharing those insights. Now, I think we've just about come to time now. So, are there any ending comments that you want to leave us with today?
Well, I'm going to go back to my first days in the company, and just to give you what a sense of what an adventure this company is. The job that I started doing in the company was recording data in furthest corners of the planet, really. Places where very few people have ever been, doing things with equipment that very few people knew even existed, and working with people whose ingenuity was, quite frankly, very, very refreshing and surprising. The can-do attitude of the company was absolutely marvelous, and loving I started loving this. Sorry about that. That shouldn't have happened. And the way those people were dealing with new ideas and new problems was absolutely marvelous. And throughout my years in the company, whether I was in Asia, in Europe, in the Far East, in the Middle East, in America, I found the same people with the same ideas, with the same will to try and resolve complex problems by trying new things. And to this day, it is still very relevant. And so I just wanted to share that CG is more than a job. It's really an opportunity for curious people to explore just how far they can go in trying to find solutions for complex problems.
Great. Thanks, Laurent, for all of those insights, sharing your time and experiences with us today. So clearly, what we first need to invent is some AI technology that recognises when you're on a live call and kind of mutes your phone. But thank you. It's been a fascinating journey to explore that technology and how that evolution is managed in this kind of industrial context. I hope those of you that have joined us have found it valuable and interesting. Thanks to everyone who's joined the live stream. I think we had a little bit of a technical thing at the beginning, so apologies for that. And if you've got some questions for us here, then feel free to reach out to us individually and keep an eye out for our next episode. That'll be coming soon. Thank you.